This program looks at electrode potentials and changes in Gibbs energy. We've seen that reactions that are spontaneous have Gibbs free energy changes that are negative. And we've also seen a variety of ways of calculating changes in Gibbs free energy. From our heats unit, we've seen the first equation. The one in the middle, we've seen in equilibrium. And now I want to introduce a third. Gibbs free energy can be calculated from knowledge of the number of moles of electrons transferred in our half reaction, Faraday's constant, and the electrode potential of our cell. Let's look at how these values fare. If we take a look at an E cell where we have a positive value, that would then give us a negative value for delta G. That would then be a spontaneous situation. If we have a negative value for our E cell, we'll end up with a positive value for Gibbs free energy, and such reactions would not be spontaneous. Let's look at a question for an example. First off, I wanted to consider the simple lead-nickel cell at standard conditions and determine the E naught for that cell. This is the equation that we use, and here's some data we see in our IB data booklet. The first thing I'm going to do is highlight the relevant equations, so the nickel and the lead. The first thing I notice that lead has a higher electrode potential, a greater tendency to gain electrons. That's going to be at my cathode, and the other reaction would be reversed and be at the anode. Substituting the values into this expression and solving for E cell, we get positive 0.13 volts, which we know is spontaneous because it's positive. Now I want to determine the equilibrium constant for this reaction. I'm going to call upon these two equations. Since they're both equal to Gibbs free energy, I can set them equal to each other and isolate them for the ln of K. Now I'll substitute in the values. Let's see a bit where they come from. First of all, 2 from the number of electrons that are transferred, Faraday's constant, which never changes, and my E of the cell, 0.13 volts. R is the gas constant, and T is the temperature in the Kelvin scale. Solving for the ln of K, I get 10.1, and then to undo the ln operation, I get K is equal to E to the 10.1, or about 24,000. Quite a large value for K, hence it favors products. Remember, questions are always welcome. Thanks for watching.